Welcome back to the course on measurement and instrumentation, and we are discussing analog meters. This is the fourth lecture of our sixth week of discussion. Today we are going to discuss another kind of meter or analog meter to measure specific quantities like power and energy. Okay. So we will start our discussion on power meters and then we will slowly move towards the tools which can be used to measure the energy consumed in household condition, and we will restrict our discussions to the single phase meters only, okay, in case of AC meters, and because the three phase meters are mostly the industry meters and mostly covered in the industrial instrumentation kind of courses. Okay. So when we talk about measurement of power, okay, first thing come in our mind is a watt meter, okay, but then along with watt meters there are other ways also to measure the power, and let's see that what can be the setup for measuring the power in DC conditions as well as in the AC conditions. Okay. So when I say power, it's basically the rate of energy consumption, and accurate power measurement is essential for a number of applications, be it in the electrical machines, in the power systems, industrial loads, and even for the energy billings. Okay, everywhere you need to require the power. Okay, so measurement of power in DC circuits and in AC circuits have little different arrangement. We'll see that how we can measure this power in two different conditions altogether. Okay, so first let's talk about power in the DC circuits. Okay. So the power taken by load from a DC supply is given by the product of the reading of a say ammeter and a voltmeter when connected in series. So for the understanding of this, we have to recall the voltmeter ammeter methodology that we have recently studied. Okay. So this was the two conditions that we have seen. The case A is something like you have load, for example. Okay. So this is the load. Okay, and this is say voltmeter across this, and this is the ammeter which is near to the load, and in another configuration we know why. Okay, we have discussed this in little detail. Okay, in case B, the voltmeter is nearer to the load while ammeter is placed over here. Okay, and now the power can be given by the multiplication of the voltmeter reading with the ammeter reading, or V into I is something we call power and the unit is watt. Okay. The voltmeter in case A not only indicates the voltage VL across the load, but in addition the voltage drop VA across the ammeter. So if I talk about this voltmeter reading, this voltmeter is not only reading this VL, right? So this V is equal to VA plus VL. And ideally we wanted like V should be equal to VL, but there is a small drop across this VA, and that's why we are getting this V as VA plus VL. Okay. So this VA is a problem for us. We have also seen this in our previous discussions also. Okay. So if RA is the resistance of the ammeter, may be very small, the voltage drop across the ammeter can be given as VA. Or say this VA can be given as the current flowing through the ammeter I into the resistance of the ammeter, which is IRA. Okay. So this VA is given as I into RA in this equation, right? Now the power consumed by the load, because we are interested in power here, okay, will be equal to the load voltage VL into the current flowing through the load, which is I. Okay. So this will be equal to VL into I. Okay. And VL from this equation, if I say from this equation, if I want to say, I am calling this equation 1. Okay. If I want to calculate this VL, the VL will be equal to V minus VA, right? So VL into I is the power consumed in the load, okay, or by the load, okay, and VL from equation 1, if I replace, okay, VL will be equal to V minus VA, and if I just reposition this equation, I can write it as VI minus VA into I, okay, and VA we have already seen is I into RA, okay. So VLI is equal to Vi into I square Ra, right? So this is, say, our second equation, okay. Now, if I see this what is Vi and what is I square Ra, okay, this Vi is the power indicated by the instrument, okay, and this I square Ra is the power loss in the ammeter. So this is Vi is the power which is indicated by the instrument, okay, and this is the power loss in the ammeter, this I square Ra, okay. So we know that power is given as V into I, or it can also be written as I square Ra depending on what form you are using, okay. So the power consumed by the load is equal to power indicated by the instrument minus power loss in the ammeter. Now, the power indicated by the instrument that we actually see, or the end user actually get the value, is equal to the power consumed in the load, okay. From this equation, if I simplify, the power indicated by the instrument will be equal to power consumed in the load or by the load plus power loss in the ammeter, okay. This equation is very, very important, and I am calling this equation 3, okay. So power indicated by the instrument, whatever power that you are seeing, is equal to power consumed in the load plus power loss in the ammeter, because V is the voltmeter reading, okay, and say ammeter is giving you a current I, okay, and that's what you will see. You will find the voltage and you will find the current, okay, and you will try to multiply it to pursue the power, okay. This was the indicated value by the instrument, and this is equal to power consumed in the load, whatever is getting consumed in the load, plus power loss in the ammeter, right. Now consider the case B, okay. In case B, I want to talk about this particular system. In this particular system, if you see, the voltmeter is nearer to the load, okay, and ammeter is far from the load, okay. So in this case, ammeter not only indicates the current through the load, but also in addition the current in the voltmeter, because say if I is the current flowing in this ammeter, okay, and if IV is the current in the voltmeter and IR is the current flowing through the load, okay, this I is equal to, say at this node, if I write the equation, Kirchhoff's current equation, I will say that I is equal to IR plus IV, right. So this is the value of the ammeter current is IR plus IV, okay. Now, so ammeter, I was mentioning, do not only indicate the current flowing through the load, but it also include the current in the voltmeter, okay. And the current in the voltmeter, if I know the resistance of the voltmeter is, say for example RV, can be given as IV equal to V by RV, okay, and I am calling this equation 4, okay. So IV is equal to V by RV, where RV is the resistance of the voltmeter, okay. Now if I calculate the power consumed by the load, okay, this will be again equal to V into IL, okay, or if I replace this IL, we have seen that I was equal to IR, or we called it for load, say for simplification we call it IL, okay, plus IV, okay, or IV can be given as I minus IV, right. So this is the current IL, right, load current. IL is equal to I minus IV, okay. So if I have to find the power consumed by the load, it will be equal to V into IL, or if I replace IL by this equation, I will get V into I minus IV, okay. Or if I simplify it, I can write V into I minus V by RV, okay, or VI minus V square by RV, okay. Now, if you see this very carefully, you will find that this value, the power consumed by the load, is equal to power indicated by the instrument. Again, this volt is the voltage which you see on the voltmeter screen, and I is the current that the ammeter is giving to you, okay. So the power consumed by the load is again equal to power indicated by the instrument, okay, this is the power indicated by the instrument, minus power loss in the voltmeter, okay. Say I am calling this equation 5, okay. So if I again rearrange this equation, I can say that power indicated by the instrument is equal to power consumed by the load plus power loss in the voltmeter, okay. So this is, say, equation 6. Now if you see this equation 3 and equation 6, they are very similar if not same, okay. So power indicated by the instrument in the equation 3 we have calculated as power consumed in the load plus power loss in the ammeter. So we have calculated power indicated by the instrument, the power that we are seeing, is equal to power consumed in the load plus power loss in the ammeter, right. And from equation 6 what we have got is power indicated by the instrument is equal to power consumed in the load plus power loss in the voltmeter, okay. In case of case A, everything is same, okay, except the third term is power loss in the ammeter, while in case B it is power loss in the voltmeter, okay. And if we see, or if we try to compare our case A and case B, okay, we see that the third term is actually relating power loss to the meter which is nearer to the load, okay. So in case A, say for example, ammeter was nearer to the load, okay. So our equation 3 was power indicated by the instrument is equal to power consumed in load plus power loss in the ammeter, okay. Now in case of equation 6, what we have seen is the third term is relating to a term, okay, which is related to the meter which is nearer to the load. Again, here in the second case, the meter which is nearer to the load is the voltmeter, right. So we have written equation 6 as power indicated by the instrument is equal to power consumed in the load plus power loss in the voltmeter, okay. So in both the cases, the power indicated by the instrument is equal to the power consumed by the load plus the power consumed by the instrument which is nearer to the load terminal, okay. So this is what we have understood from this discussion, okay. So in case of the AC, okay, we are more interested into the average power, not in the instantaneous power, okay. Let's try to understand this, okay. The instantaneous power varies continuously as the current and voltage go through a cycle. In case of, say, AC signal, we are not interested in the instantaneous value of the power, okay. Of course, there are conditions like if the transient conditions are getting studied, in those cases you are more interested in the instantaneous value rather than the average value. But in general, we are interested in the average value over a cycle for quantities like power, okay. This is because the average power, when it is multiplied by time or if it is taken over a certain time period, okay, it measures the transfer of energy over a time interval, okay, if the steady state conditions exist, okay. Now in place of this voltmeter ammeter configuration, a wattmeter can give you a direct indication of power and there is no need of multiplying two different readings taken by two different tools, okay. So one thing is very clear that a wattmeter can multiply the voltage and current to obtain the power consumed, okay. So in the voltmeter ammeter method, we are doing it separately, a wattmeter can do inherently, okay. Again, there are some other problems also, like for example, if I talk about instantaneous power, it can be simply given as a power equal to voltage into current, where say take this equation, I am calling this equation 7, okay. The power P, V and I all are the instantaneous values. So this instantaneous power is equal to the instantaneous value of voltage when it multiplied with the instantaneous value of current at particular time, say t equal to t1 for example, okay. Now if both current and voltage waves are sinusoidal, the current lagging in phase by say angle phi, then we can simply write as say V is equal to Vm sin omega t, and since current is lagging behind this voltage, I can write I is equal to Im sin omega t minus phi. I am calling this equation 8 and this I am calling equation 9. So in this case what we are seeing that current and voltage are sinusoidal, okay, and current is lagging behind the voltage by a phase angle phi, okay. Now if I have to calculate the instantaneous power, I will simply multiply them, okay. So instantaneous power P can be given as V into I, or if I multiply them I will get Vm into Im into sin omega t into sin omega t minus phi, okay. If in this equation, okay, I am calling this equation 10, okay, if omega t is equal to phi equal to theta, okay, this can be written as P is equal to Vm into Im sin, this can be written as theta, this can be written as theta, or this P can be written as Vm into Im into sin theta, okay, into sin theta minus phi, alright. Okay. So this is sin theta into sin theta minus phi. If I simplify this, okay, this instantaneous power can be written as Vm into Im by 2 into cos phi minus cos 2 theta minus phi. I am calling this equation 11. Okay. So the instantaneous power is equal to Vm into Im by 2 into cos phi minus cos 2 theta minus phi. Alright. So in the AC circuit, the instantaneous power, which is of course a function of time, varies continuously with time because both Vt and It is also varying in time. Okay, so the Pt will vary continuously over a complete cycle, similar to what Vt and It is doing. Okay, so in steady state AC analysis, the instantaneous power, which is of course power at a specific moment, varies continuously with time. Now, because the instantaneous value oscillates between positive and negative, it is not very useful for practical consideration or practical analysis. Okay. So basically instantaneous power, sometime it is important, particularly in the condition where you are studying some switching operation, or you are trying to do sudden load changes, or if you are doing if there is certain fault in the power system. In those cases instantaneous power might be useful, but in more practical sense it is the average value which is more desirable. Okay. So in steady state operation, the main interest is again in the average power over a complete AC cycle. Okay, and average power actually represents the net useful power actually delivered to the load. Okay, so that's why it also help in calculating energy and other parameters. We'll discuss that later on. Okay, but average power actually indicates the real energy consumption. It also relates to the heating effect of the AC signal, okay, and it is the actual work done by the circuit. Okay, so that's why we are more interested in the average power rather than bothering about the instantaneous power. Okay, so the average power when multiplied by the time or when integrated over the time in more practical sense represents the total energy transferred during that particular interval under the steady state operating conditions. Okay, so the instantaneous power again can be given as we were discussing, Pt equal to Vt into It, where P, Vt all are the instantaneous value of power, voltage and current that we have seen. Okay. Now if we have seen that when the voltage and current are given as Vm sin omega t and current as another signal, another sine wave which is lagging say with the angle phi that we were discussing, okay, I can be given as Im sin omega t minus phi. Okay. Now Pt we have already calculated it as Vt into It, or this can be given as Vm Im sin omega t into sin omega t minus phi. So we were calculating this power, okay, and we have came to a term which is equal to Vm Im by 2 into cos phi minus cos 2 theta minus phi, and this was what we have got from our discussion on the average instantaneous power basically. Okay. So from equation 11 we have reached to this value. Okay. Now if I have to calculate the average power, okay, so this was our equation 11. Okay, so then if I have to calculate the average power over a cycle, okay, this can be simply given as Vm Im by 2 pi, okay, and then integration from 0 to 2 pi. So what basically we are doing is we are integrating it over 0 to 2 pi and then averaging over the complete cycle, right. So again what we are doing is basically 0 to 2 pi, okay, p 1 by 2 pi into say d omega t, for example, okay, or say d theta, because we have considered omega t as theta, okay. So if we do this, okay, we will get the average power over a complete cycle, and this can be given as Vm by Im by 2 pi and then integration from 0 to 2 pi, then this function as half cos phi minus cos 2 theta minus phi into del theta, and if you integrate you will get Vm Im by 2 into cos phi, okay, and say this is equation 12, okay, and this is the average power over a cycle, particularly for the AC signal where V is equal to Vm sin theta and the current was lagging by a phase angle say phi with the voltage, okay. Now this equation can be simplified as P is equal to Vm by under root 2 into Im by under root 2 into cos phi, okay. Now these two values Vm by root 2 and Im by root 2 are nothing but the root mean square values, and we call it V and say we call it I, okay. So the average power, now I am denoting it with the capital P, is equal to V into I into cos phi, where V and I are the RMS values of voltage and current and cos phi is the power factor of the load. So the power factor now cos phi is involved in the expression for power. This is the power in the AC circuit, and we have named equation till 12. So we will call this equation, we are calling this equation as equation 13, okay. So the average power in this AC circuit is given as V voltage into or the RMS voltage into the RMS current into the power factor, all right. Now the power factor is involved in this case in the expression for power, means that in AC circuit power cannot be accurately measured using only the ammeter and a voltmeter. So the method that we have extended to for the DC cannot be used here, okay, because this method does not consider the phase difference between voltage and current, okay. So if there is any phase difference phi between the voltage and current, the ammeter voltmeter method will not take that into the consideration, okay. And you need a specific tool to measure this power, which can multiply the voltage into current value with another factor, which is the power factor or the cos phi value, okay. And therefore a wattmeter is desired here, okay. So a wattmeter is therefore required as it directly measures the true power by accounting the power factor in the circuit. So wattmeter will definitely give you a value which is V into I into cos phi, and we'll see how wattmeter actually gives this value, okay. And for understanding that, let's try to understand a class of wattmeter which is say based on electrodynamometer principle, or we call it electrodynamometer wattmeter, okay. So let's discuss our wattmeter which is based on electrodynamometer, okay. We have already discussed principle of electrodynamometers in our previous classes. You can go to that particular lecture and try to understand what the electrodynamometer was doing, okay, and what is the basics of its operation. And if you come back to this particular lecture, it will be more interesting and you will be able to connect with this more, okay. So electrodynamometer wattmeters is very similar to the electrodynamometer type of ammeter, okay. So if I recall it, what we have seen there, we had coil configuration like this, okay. So we had a fixed coil, okay, and then we had a moving coil, right. So this was the fixed coil, for example, okay. So this was divided into two different part, okay, in series configuration to have maximum flux at the center, if you remember, so that more flux linkage can happen to the moving coil, okay, and this was the moving coil. So this is fixed coil and this was the moving coil, okay. And if say this current flowing through the fixed coil was say IF, and in the moving coil say it was IM, the deflecting torque was proportional to IF into IM, okay. In fact, for the AC signal we have seen that TD was even proportional to IF, IM and the cos of the phase difference between them, okay. And this is the basis behind the AC electrodynamometer kind of instrument, okay. So if you remember, the deflecting torque particularly was equal to, in more precise way, was equal to I1 into I2 into cos phi into dm by d theta, and if you recall, this m was the mutual inductance, okay. And if say control is getting provided by the spring system, okay, so Tc is given as k theta, where theta is the deflection and k is the spring constant, and if we equate these two equations at the equilibrium condition, Tc is equal to Td, okay, in that case k theta is equal to I1 into I2 into cos phi into dm by d theta, or the deflection was equal to I1 I2 by k into cos phi into dm by d theta. This is what we have already seen in case of the electrodynamometer kind of instrument, okay. Now deriving from this, okay, we have AC or the electrodynamometer kind of wattmeter, which is having very similar configuration, okay. You can have a look that this is a configuration of the actual wattmeter, okay. We have a fixed coil, okay. You can see that this is the series configuration of the fixed coil and this is the moving coil, okay. And current is passing through this fixed coil, okay, and voltage across the moving coil, okay. So if I have, say for example, since you require 4 different terminals because you want voltage as well as current, okay. So if I have, okay, a configuration like this, okay, so these are say terminals of the fixed coil, okay, this is the terminals of the fixed coil and these are the terminals, okay, of the moving coil, okay, these are the terminals of the moving coil, okay. Current is, it is being allowed from this, okay, and voltage say is allowed from this, okay. So if I want to redraw it, okay, or say if I want to modify our previous drawing, okay, now this is say C1 C2, okay, from the fixed coil, okay, and say this is we call P1 P2, okay, C1 C2 and P1 P2 for voltage and this is for current, okay. The fixed coil, sometimes also known as field coil in case of the wattmeters, are connected in series with the load and so carry the current in the circuit, okay. So the current is flowing through the fixed coil, okay. Now since it is carrying the current, the fixed coil is also sometimes called as current coil, CC of the wattmeter, okay. So the similar configuration is being used as an electrodynamometer, but what we are doing is we are now calling the fixed coil or the field coil, which we were calling in case of electrodynamometer, we are calling it as a current coil or the CC coil, okay. Now the moving coil is connected across the voltage, okay. So this is the load, okay, say RL, okay. I want to calculate power consumed by this RL, okay, and I have a wattmeter, okay, which is having say this as a current coil, okay, I am calling this CC and this complete thing is say wattmeter, right, and I have a moving coil inside, okay. Fine. So this current coil will be connected say somewhere here, okay. So I will have like this, okay. So current is flowing through this current coil, okay, and the voltage, this moving coil which is giving the potential, okay, is connected say across this, okay, which is shown over here, okay. So you have this current coil connected like this, okay, like this, okay, so that the same current flows through this as in the load, okay, because this is what you are getting, which has to be multiplied with the potential, okay, and the moving coil is connected across this load so that the same voltage is dropped across it, okay. So the moving coil is connected across the voltage, therefore carries a current which is proportional to the voltage. So a high non-inductive resistance is connected in series with the moving coil to limit the current to a small values, and this small values is around typically in the range of say 100 milliamp or so, okay, because the moving coil carries a current which is proportional to the voltage, okay. Since it is taking care of potential, okay, we call it pressure coil or voltage coil or sometimes potential coil, okay, or simply PC of the wattmeter. So two coils we have seen for the wattmeter. One is the CC, which is the current coil, and the second is the pressure coil, which is the PC, okay. Now the fixed coil carries the current of the circuit, okay, and they are divided into two halves, very similar to what we have done in the electrodynamometer, okay. The reason for using fixed coil as current coil is that they can be made more massive, okay, because they can be easily constructed to carry high amount of current, okay. So the order of the current that it can handle is of the order of typically 10 to 20 amps also, okay. But for carrying very high current out of this current coils, they are insulated so that any kind of eddy current induction and other things are avoided, okay. The moving coils is supported on a pivoted spindle and is fully enclosed within the magnetic field produced by the fixed current coils, okay. The spring control is used for the movement, okay. Since the current of the moving coil is carried by the instrument springs, which are phosphor bronze springs, it is limited to value which can be carried safely by the spring without appreciable heating, okay. If it is heated, it can break also because phosphor bronze doesn't have that much strength, okay. So what we have seen just now is the spring control is the carrier for the current, okay, and that's why the current is limited to around 100 milliamp or so, okay, in the moving system, okay. So the control is provided by the spring system, damping is provided by the air friction, okay, and the scale and pointers of these power meters or watt meters are equipped with mirror type scales and knife edge pointers to remove reading errors due to parallax, okay. The instantaneous torque of an electrodynamometer instrument we have already seen in case of generic statement, as the instantaneous torque was given as I1 into I2 into dm by d theta. The cos phi term we have seen in our discussion when we were studying this current values specific to the sinusoidal waves, okay. So the instantaneous torque of electrodynamometer instrument is given as Ti equal to I1 I2 dm by d theta, okay. This was a generic statement when we are not considering any sinusoidal or another wave. So we are calling this as equation 14, okay. In this case, I1 and I2 are the instantaneous values of current in the two coils, okay. Now say let V and I be the RMS value of the voltage and current which is being measured. The instantaneous value of voltage across the pressure coil circuit can be simply given as V, which is equal to say root 2 into V sine omega t, okay, and say this is our equation say 15, okay. So this is the instantaneous value of voltage which is across a pressure coil, okay. So if the pressure coil circuit has a very high resistance, it can be treated as purely resistive circuit, okay, and current IP in the pressure coil is in phase with the voltage and its instantaneous value can be simply given as IP equal to V by RP, okay, or V we have just calculated as from our previous equation as root 2 V into sin omega t from equation 15, okay. So IP can be given as V by RP, okay, where RP is the resistance of the pressure coil circuit, okay. IP is equal to root 2 V by RP into sin omega t or root 2 IP sin omega t. I am calling this equation 16, okay. So in this case V by RP is the RMS value of current in the pressure coil circuit and RP we have seen is the resistance of the pressure coil circuit, okay. Now if the current in the current coil, okay, lacks the voltage in the phase by say angle phi, instantaneous value of the current through the current coil can be given as IC equal to root 2I sin omega t minus the phase lag which is phi, okay. So I am calling this as equation again say 17, okay. Let's recall from our previous equation which was equation 14, we have seen that the instantaneous value of torque was given as I1 into I2 into dm by d theta, okay. So if I recall that equation of instantaneous torque, Ti equal to I1 into I2 into dm by d theta, okay. I1 is IP, I2 or the current in the pressure coil, okay, I2 is the IC value, instantaneous value of current through the current coil, okay, IC, okay, which is given by equation 17 and this was IP was given by equation 16, okay. If we put these values in this equation, okay, what we get is Ti is equal to root 2 IP sin omega t into root 2I sin omega t minus phi into dm by d theta, okay. So if I simplify this, okay, Ti is equal to IP into I cos phi minus cos 2 omega t minus phi into dm by d theta, okay. Now the average deflecting torque is equal to 1 by t integration from 0 to t Ti into d omega t or the instantaneous value of the torque into d omega t. Td can be given as 1 by t integration from 0 to t and this particular value from Ti, say I am calling this equation 18, okay. So the value of Ti from this, okay. So Td can be given as integration of this value from 0 to t over 1 by t, okay. So this Td value can be given as 1 by t into 0 to t Ip into I cos phi minus cos 2 omega t minus phi into dm by d theta into d omega t, okay, and this equates to Ip into I cos phi into dm by d theta or V by I by Rp into cos phi dm by d theta. This is say equation 19, alright. So the deflecting torque is equal to Vi by Rp into cos phi dm by d theta and the controlling torque exerted by the spring we know that is given as Tc equal to k theta, okay. So this was say equation 20 where k is the spring constant and theta is the final steady state deflection, okay. So since the moving system of the instrument cannot follow the rapid variation in the torque, okay, because the torque has twice the frequency, it will take up a position at which the average deflection torque is equal to the restoring torque of the spring, okay, and at that balanced position k theta is equal to the torque value or Ip into I cos phi into dm by d theta, okay, or the deflection can be given as Ip into I cos phi into dm by d theta over k, okay. So if you simplify this, you will get theta is equal to V into I into cos phi by Rp into k into dm by d theta, okay. Now if I consider k1 as say another constant which is equal to 1 by Rp into k, okay. So if I replace this value say 1 by this value, okay, as k1, okay. So this can be written as deflection equal to K1 into Vi cos phi into dm by d theta. Okay. Please note that this Vi cos phi is equal to the power which is being measured. So the deflection is equal to, so this particular value K1 into dm by d theta, okay, into the power which is being measured, right. So deflection is equal to, deflection is directly proportional to the power that is measured, all right. So this is how a simple electrodynamometer kind of wattmeter works for the measurement of power, all right. Similar to this, we have our discussion on measurement of energy, okay. So all of us know what is energy. Energy is the total power delivered or consumed over a time interval, that is energy is equal to power into time. We have just seen that power, particularly for the DC setup, we have power is equal to V into I. So energy can be given as V into I into T in a more generic term, okay. So electrical energy can be represented as an amount of work done or as a heat produced in a electrical system, okay. So in more generic term, the power can be, or the work done can be given as V into I integration over a time period, so 0 to T, okay, over certain time, okay. In this case, say this V and I are the voltage and currents, okay. The unit of energy is joule or watt second, which is 1 watt over an interval of 1 second. But usually we do not use this kind of terminology in our day-to-day discussion. We usually have one unit which is nothing but a kilowatt hour, okay. So energy meter basically measures the electrical energy consumed by a circuit or a load over time, usually expressed in kilowatt hour, and this kWh is more general term that we as a layman are also exposed to, okay. So it is the energy consumed when is delivered at an average rate of say 1000 watt for a hour, okay, or for 1 hour, okay. So based on the type of supply, energy meters are broadly classified into DC energy meters and AC energy meters, okay. Now DC energy meters are also of various type like electrolytic meters, motor meters, clock meters, then intermittent registering meters and so on, okay. And AC meters again are divided into single phase meters, three phase meters and so on, okay. But in this course, we will be discussing two different meters. One will talk about the motor meters, okay. Motor meters are kind of energy meters which are used to measure electrical energy in both DC and AC circuits, and they operate by continuous rotation of the moving system. Please note that when I say continuous rotation of a moving system, it is not similar to the indicating instrument, okay. So it is unlike the indicating instrument which only deflect through a small angle, okay. What I am trying to talk here is actually a moving system where the speed of rotation is proportional to the measured quantity, okay. So measured quantity is, say for example, power for watt hour meters or current for ampere hour meters, okay. And the total number of revolutions represents the total energy consumed defined using a meter constant. So it's kind of revolution per kilowatt hour or so. So this is how generic motor meters are defined, okay. In our next class, we will be taking this motor meters, and we'll also continue our discussion on energy meters for AC signal specifically, particularly the single phase induction kind of energy meter. So induction meters are helpful here. So we have discussed induction meters in our previous classes, where we have seen that there are two coils and there are two fluxes associated with it, and each flux is linked to another current, and that's how this induction instrument actually operates, okay. So we will continue our discussion on power and energy in our next class, and we will specifically discuss the energy meters, okay. So thank you.